Okay, last time we were talking about the time complexity to measure the efficiency of an algorithm or a particular data structure, and during that I told you that the time complexity is not just of an algorithm, but it is of a piece of code as well. For example, this is a piece of code, right? And this piece of code utilizes a data structure. For example, it utilizes a linked list, right? And it utilizes basically a linked list maybe to store the data or retrieve the data and use it for multiple manipulations. So we'll be interested in the performance evaluation of both this code. Okay, this should be blue. This code and this data structure. When we analyze the performance of this piece of code, we will be interested in we will be interested in time, right? We will be interested in making sure that this code consumes the minimum amount of time. But when we are analyzing the performances of this data structure, we will be interested in space, and our goal will be to minimize the amount of space which is required by this data structure. Or for that matter, if we excuse me, I'm having a sore throat, so I'm trying to cope with that. So you may get disturbed for a while, but excuse me for that. So when we analyze the performance of the code or the data structure, and we come to know that the piece of code is consuming more time, or a piece of data structure is consuming more space, then we take corrective action. But remember that we always have a trade-off between time and space. By trade-off, I mean if you want to minimize the time, then it will result in maximizing in the consumption of the space. But if you want to minimize the consumption of space, this is going to result in maximizing or increasing, for that matter, the consumption of time. But later I'll be giving you a few examples where you will be able to understand this trade-off between time and space. So it is quite challenging for a piece of code to minimize its time and its space simultaneously at the same time. So it's quite challenging. So previously we talked about what an algorithm is. So an algorithm is a finite set of statements that guarantees an optimal solution. By finite, we mean that there should be no such piece of code in your algorithm or few statements in your algorithm that should take it into an infinite loop. And by guarantee, we mean that if the piece of code or the algorithm is working on Core i7 machine, then it should work on Core 2 or Pentium 3 or Pentium 4 as well. And if you coded or if you developed your piece of code for Macintosh operating system, it should work for Windows and Linux and Unix as well. And by optimal, it means that the solution which your algorithm should provide should be perfect. It should not be near to optimal, it should be the optimal one, right? So instead of repeating this stuff, because the previous lecture is already available online, so let me directly go to the statement which go to the slide which we covered the last time. From there we will continue, and we were analyzing this piece of code. And the first task in analyzing the performance of the piece of code is to find the set of statements, basic statements, or which are being executed. So if you see here, this is the statement number 1, which which assigns a default value or an initial value to a variable. Then we have for loop, which has 3 statements: initialization, condition, and increment or decrement. So these are 3 statements, and then in this particular line we have 3 statements: the assignment statement or assignment operation, the increment operation, and the array access operation, right? And then we have the return operation or function or whatever you call it. So if you see here, 3 of the operations, that is statement number 1, 2, and 8, are being executed only once, whereas 5 of the statements, which are statement number 3, 4, 5, 6, and 7, they will be executed n times, because this statement is within this loop, right? So so this piece of code will be executed n times. So this makes our equation to be 5n plus 3. So this will be our equation. Now this equation represents the number of steps that this piece of code is going to consume, right? So this is the function f of n is equal to 5n plus 3. Now if I plot this in the Microsoft Excel, okay, let me draw it from scratch for you. For example, this is the n and this is f of n, and for example the array size is 10, and for example later the array size becomes 20, then it becomes 30, and let me stretch it up to 250. Then the f of n, which is if you see here 5n plus 3, so it will be 5, and this is the value of n, is equal to 5n plus 3, right? So this is the this will be the value of f of n when we paste when we put this value in the function f of n, where f of n is defined here, right? So let me drag drop, because it will automatically compute these values. And now if you plot the graph, here, if you plot the graph of this, now let me remove it, and okay, and if you see, okay, let me do a quick layout for you. Primary x-axis and primary y vertical. If you see steps, these will be steps. This will be size of. This will be size of. Okay, where input, right? And these values needs to be updated as well, because there is a jump of 10, 20, 30, right? So and this will be. Now if you see here, as the size of the input increases, the requirement of number of steps is also increasing. But if you see here, this is increasing linearly. So this is a linear growth. For example, if we had some other function, for example, our f of n here is equal to 5n plus 3. For example, if we had another function f of n which were like log of n, and I'm sure this yellow won't be very much visible to you, so this line would be like this. So this is a logarithmic growth, which is less. And then for example, if we had another function which was like f of n is equal to n raised to power, let's say 3, so that will be like something like this. Now if if we analyze these three functions, and don't worry about that how this or this function will be achieved. I'll be giving you examples where we will have a piece of code, and I will explain to you how these functions are created. But for the current example, I hope it is clear that how f of n is equal to 5n plus 3 has been achieved here, right? Now, explaining these graphs, okay, and I rubbed that. Let me draw them again. For example, this was an exponential growth graph, and this was a logarithmic growth graph. Now, if you want to see that which one is better or which one is worst, if you see, as the size of the as the size of the input increases, the number of steps required by this yellow line is far less than the number of steps required by this blue line, or for that matter, for number of steps required by this red line. So this line, this yellow line is the apparently is the best, right? And among these, the worst one is this red one, right? So and I'll be giving you more examples later in this course where you will have a good idea. But again, coming back to our example, this piece of code has a complexity function of f of n, which is equal to f5n plus 3. And instead of explaining the linear growth here, I drew the graph in Microsoft Excel for you, and I hope that was more comprehensible. Now, if you further analyze the equation 5n plus 3, then you will notice two things, that one is 5 and the other one is 3. We are always interested in having a big picture. For example, let me just take the case of this plus 3. Now, this plus 3 is insignificant, right? This is insignificant. For example, let us switch ourselves to the discussion of analysis of code or algorithms to a different example. For example, if you see a mobile phone with me, for example, I am teaching a class and I bring with myself a new mobile phone, and some student, this is a nice student, and he saw my mobile, for example this new mobile, and he was like, oh, I want to purchase this mobile, right? And after the class he meets me and asks me, okay sir, from where have you purchased this mobile? And I for example, I tell him that from XYZ shop I have purchased it, and he says, okay sir, I want to purchase it as well. What is the cost of this mobile, right? And for example, I tell him that it's like for example 29,501, right? So this is the for example rupees. So this is the cost of this mobile, right? Okay, this is the cost of this mobile, and this guy goes to the shop and gives him 29,500 rupees, and he searches for this 1 rupee in his pocket, and there he cannot find it, but the shopkeeper says, okay, leave that 1 rupee. So that 1 rupee, this 1 rupee is what? This 1 rupee is insignificant for the shopkeeper and maybe for this guy purchasing the mobile phone, because he has already spent 29,500 rupees. So 1 rupee does not matter here. So that is insignificant. Giving you another example. These shoe stores, they sell shoes, and I'm trying to. Oh, this is not a shoe. Okay, let me try a new shoe. Try to draw a new shoe. Now this looks like a bit of a shoe, right? And these are the laces as well, right? So, and it says, okay, this costs around 599. This is the cost of this shoe. What if you go to the counter and you pay like 600 rupees, and most of the time 99% of the cases the shopkeeper him or herself does not return you 1 rupee, and you don't bother about taking your 1 rupee back when you have given the shopkeeper 600 rupees, because that 1 rupee is insignificant for you. So same goes here, that this in this 5n plus 3, this plus 3 is insignificant, right? Now coming back to this example, if you see here, in the 5n plus 3, let me remove this plus 3 term, right? Let me remove this plus 3 term. Okay, the line, if you see, this line has bended a bit, but if I drag and drop this whole line, because this whole curve will change, and if you see here, there is no difference in the curve, the trend remains the same. So this plus 3 had no effect on the bigger picture which we were getting. So this plus 3 in the 5n plus 3 is insignificant. Now coming to the other term, which is 5. Now this 5 is basically inaccurate. Now why do I say that it is inaccurate? Now for this we have to go back to the code example which we discussed. Now if you see here, now this 5 represents statement or operation number 3, 4, 5, 6 and 7. Now if you see the operation number 3, this is a logical operation, right? And if you see operation number 4, this is an increment operation, right? And if you see operation number 5, this is an assignment operation, right? Not going any further, if you see this operation, this operation and this operation, all these 3 operations are different operations, right? It means that these operations are going to consume different amount of CPU time. For example, this may consume 1 cycle of the CPU, and when I say cycle, there is a different course. Maybe you are registered in that course in the present semester, or maybe you are going to register in that particular course in the next semester, which is called Computer Organization and Assembly, where you will actually learn how this code, the binary code, is fetched, it is decoded, and it is executed in the on the machine itself, the processor itself. So without going into the detail of that, this actually has any statement which executes runs under a cycle which is called fetch, decode and execute cycle, right? Now each operation requires different number of fetch, execute and decode cycles, right? For example, again I cannot exactly recall. For example, this logical operation may require 1 cycle, fetch, decode and execute operation. For example, if there were a multiplication operation, then that would require maybe 2 fetch, decode and execute cycles on the processor itself. So it means that if what we have done, we have assumed that all of these 5 operations, state operation number 3, 4, 5, 6 and 7, they are consuming the same number of fetch, decode and execute cycles, but actually they are consuming different number of fetch, decode and execute cycles. So that is why we say that this 5 is inaccurate. And again, as I told you previously, this plus 3 is insignificant. So what remains with us is this n, and this n tells us about the big picture of the algorithm, that how or what will be the behavior of this algorithm, right? So as n gets larger, the plus 3 becomes insignificant and 5 is inaccurate, as I explained to earlier. So what is fundamental is that the time in case of the algorithm which we are discussing is linear in n, right? So any linear algorithm will tend to perform like this particular line, right? Now coming to the asymptotic complexity, as n gets larger, concentrate on the higher order terms. And mind it, I have not explained the term asymptotic complexity yet, right? And I'll be explaining to you that shortly, right? Now we will drop the plus 3, we will drop the n, we will drop the constant coefficient with n, and what remains with us will be only the term n, which we will be concentrating on. Now be careful, this is extremely important, be careful, differentiate between the two terms, that is performance and complexity, right? What performance is? Performance is the actual amount of time and maybe the memory which an algorithm consumes, and complexity is the amount of resources of a program or algorithm which an algorithm requires to solve a problem. Okay, and that was a bit dry. Let me try to explain it to you. For example, okay, let us draw here a player. This is a cricket player, right? And okay, this is a bat. I'm trying to make a bat, so this is a bat, right? Oh, so assume this is a cricket player, right? Cricketer, right? Now, for example, he plays a match. He plays a match M1, M2, M3. Right? He plays, and in the first match, he makes a score of, he makes runs. Let's say he makes 30 runs. And in the second match, let's say he is out on 0. Okay. And in the third match, he ends up making 150 runs, right? So if we want to gauge the performance of this player, then in terms of number of runs which he made, then his performance is 30, 0 and 5 in these 3 matches. And again, you can compute the average of this player as well, right? Now, to measure the performance, this player has to play the game. Without playing a match or an innings, we cannot measure or we cannot gauge his performance, right? So this was about performance. Right, okay, ये तो चलो खैर while I was typing, I was not looking at the screen, so excuse me for that. So this was all about performance, and now let us discuss the complexity. Right now, let me repeat: to measure or to gauge the performance, this player has to play the game. Without his playing the game, we cannot gauge, we cannot measure his performance, right? For example, in another scenario, we have another player, right? This is a player and he has long arms and he's tall, and okay, and he has big muscles, right? And his age is like, for example, he's a young man or maybe woman. His age is like, let's say, okay, 21, okay, okay, and now, and maybe he has a previous record of playing for his district team, right, and his sugar level is, for example, okay, we conducted his different tests, and we found that he is not overweight. Okay, let me type it instead here. He's not over he's not overweight, right? And for example, he has been playing different sports, right? And now if we want to gauge the performance of this player, sorry, not performance, if you want to gauge the complexity of this player, for example, in match 1 and in match 2 and in match 3, what we are going to do is that we are going to predict the complexity, that as the number of matches increases, and then as this guy plays more and more matches, his performance is either going to increase, or for that matter his performance may decrease, right? So what complexity represents? Complexity in terms of algorithms. So before going to the world of algorithms, let me summarize what I have tried to explain here, that for the sake of performance, for the sake of computing the performance, we need to play the game physically and actually, and then the score, whatever score which we consume or we achieve, or whatever score we make, is our performance. But the for measuring the complexity, we don't need to play the actual game. Instead, based upon our features, based upon maybe our health or previous history, sports history, we need to predict about the performance in the game without actually playing the game, right? So now let us come to the world of algorithms. That for example, if we have a piece of white control, right, if we have this piece of code, and if you run it, if you run it, then you will have two things, right? One is the time, and the other one is space. For example, it consumes, let's say, 3 seconds in terms of time, and it consumes 10 KB of memory, right? So this is the performance of this particular algorithm, right? But if we have another piece of code, and you want to find the complexity of this code, then what happens, that you don't run it, or you don't execute this this particular algorithm. Instead, you analyze this piece of code and you draw a graph. This will be the size of the input, and this will be the number of steps, and then you analyze it using the asymptotic analysis of the code, or the code analysis, which I gave you an example of, where we had a complexity function of f of n, which was 5n plus 3, right? So using that, we can analyze the complexity of the code. So when we analyze the complexity of the code, we do not run the program actually, rather we analyze that as the size of the input increases, how much will be the increase in the number of steps that this particular algorithm is going to require. So this is the basic difference between the performance and complexity, right? So we need to be careful about that. Let me read it out again. By performance, we mean how much time, space, memory an algorithm is actually consuming or has actually used when a program is run. This depends on the machine, compiler, and so many other stuff. But in complexity, we need to know that how do the resources required for a program or an algorithm scale. So in complexity, we basically measure the scalability of the algorithm, that as the size of the input increases, how much is the increase in the number of resources required by the particular algorithm, right? So that is sufficient for this lecture, and we will be carrying on this with this example in the next lecture, and I will be explaining the asymptotic analysis or the asymptotic complexity of the code.